Welcome to the video lecture. Today I am going to explain energy and coenergy in a single excited system. So, for understanding I am taking here a simple magnetic relay. This magnetic relay having one of the magnetic core, this is called as a magnetic core, this is the mobile magnetic armature. This coil, a number of turns coil is excited with this voltage source, it carries the current, and into I it set up the here in this one magnetic flux by some flux phi. So, initially this plunger is available, there is no air gap touched with this core, but due to this flux we are following maybe the similar force, that is why automatically it experiences the mechanical force, the plunger is moving a little bit distance of x. So, at the time the variation of this air gap, automatically it requires more current to set up the magnetic flux, rate of change of current is occurred. So, rate of change of current it develop the voltage across this coil with some flux linkage here the lambda. Okay, you know this equation, you know that the energy stored energy that equal to WFLD is the state function of lambda, actually here it is lambda comma x is equal to here id lambda minus force into dx, it is the energy balance equation in this equation, but how it is getting here. So, once you give the supply here, so automatically the flux is set up. In the setup here the energy stored, that energy value is equal to id lambda minus ffld dx. But how it is changed initial, for example with respect to I, suppose once the current rate of change of current causes the rate of change of lambda. So, why? Because this is the function. In this case but I equal to 0, lambda equal to 0. So, there is no flux linkage, initially V equal to 0, I 0, at that time there is no lambda, but I is increase, lambda is also increase, but it is a non-linear system, iron core is the non-linearity, that is why it is set up from 0 values to a particular function lambda, new values lambda comma I. So, but how to calculate this energy? This energy by mathematically. So, we are taking this graph, you can 0, you can give the names, it is A, B, C. Here area of in this area, yes, the state variables are changed from 0 to some lambda and it is 0 to some I. You want to calculate, that means it is varied like this, here this portion. So, this is called as a d lambda. So, integral of id lambda we are getting energy, that formula, that is why it is called as it is a portion of triangle OAB, this portion is called as a field energy. So, here in this perspective actually this is the energy, but mathematically these values maybe the point is changed in this area also, you have to take small distance of di in terms of I di, we can write it like this. So, di this portion you have to calculate this portion, that is called as, this is another term I am giving, that is called as a coenergy. So, here field energy you already know this, the lambda function of lambda comma x. Here both field energy and here WFLD dash, WFLD and WFLD dash is equal to what is the value? This portion is called as a triangle from the figure, triangle OAB, or otherwise from the portion of OAB, and maybe it is the portion is called as, the area of this portion is called as field energy. The area of this OBC is called as the coenergy. Total value, that means total area, area of OA, BC and O, entire this is called as, this is called as I, this is called as lambda. So R is equal to lambda I. This lambda is equal to entire the upper portion of this curve is called as a field energy. The down portion of in this area is called as a coenergy. So lambda is equal to, we are call it as field energy plus coenergy. Lambda is equal to field energy plus coenergy. Yes. Now you know this field energy plus coenergy is equal to I lambda. My aim is to calculate the coenergy. So we already know this field energy WFFLD is equal to ID lambda minus force into dx. Maybe it is called the equation 1, this is called as equation 2. 2 is substitute in equation 1. What is the value? Coenergy is equal to I lambda minus from equation, yes, what is the field energy? ID lambda minus FFLD dx. Yeah, so from this one, coenergy is equal to I lambda minus WFFLD. So I lambda minus WFFLD. This is the WFFLD. So you can simplify this. I think ID lambda minus, sorry, yeah, this is called as, it is a differential equation. You know this is the differential equation, this is the normal equation. So I directly not write this. Now first of all, for equation 1 both side, apply the derivation. Now differentiation d I lambda is equal to d WFFLD plus d WFFLD dash. Yeah, from this equation, what is the, it is a UV formula. Yes, we can write this like this, ID lambda plus lambda di is equal to field and co-field dWFFLD dash. My aim is to calculate coenergy equal to, you know, field energy is already equation 2, we write it this, ID lambda minus FFLD field force into dx. Yes, this is the field, this is substituted in the right side, this is sent to left side, we can get it now, minus ID lambda minus lambda plus lambda I, sorry, lambda di. Please try to understand, I have written this equation, just I have to send this side. So whether it is dWFLD dash is equal to, dWFLD is nothing but this one, and you already this is available. So okay, we can write it like this or otherwise, and you can provide this minus, whatever, the both are same, minus ID lambda minus into minus plus FFLD dx plus ID lambda plus lambda di. Here these two terms are cancelled. Finally here it is getting lambda di plus FFLD dx. Now this is the state function, It is varied with two variables, that is called as I comma x. So my conclusion, actually why these are the two terms we are introduced. One is the energy and coenergy. So any magnetic material having the core iron core material, or otherwise the core air core or iron core, whatever may be, but air core is the linear system, iron core is the non-linearity. It is excited, it energy stored, that stored energy value is equal to I d lambda minus FFLD dx. So by using this equation we calculate the magnetic force in this system, and maybe it is a rotational system, we have calculated the torque also. But it is a pure mathematical, we compare this, one is the field energy, another we are getting the coenergy. Coenergy is the, it is also one term we are getting lambda dI plus FFLD dx. Here the coenergy is a function of I and energy is the function of lambda. So by using sometimes the coenergy, the torque or maybe the force is easily calculated in particular calculations, maybe some other excited. So it is a pure it is a the phenomenon. Either you can use energy, we can calculate the force and torque, or using coenergy we can calculate the force and torque of the particular system. But which one is selected, that is it depends upon our simplicity in the mathematically. So that's why sometimes we derive the equations, either force and torque equations from energy, sometimes we are calculating the force and torque from coenergy also. That is depends upon the, especially it is the single excited, maybe it is not a big issue, but once the system is complicated with the double excited and triple excited, at the time this direct energy, it is somewhat is complicated. That's why we are taking from the coenergy we can calculate the either force and torque equation. So this is the pattern. We can define this coenergy is nothing but it is a state function. It depends upon the two state variables. One is called as I, another one is called as the x. Thank you.